The frequency effect is very noticeable. If you take red light and blue light, they have different frequencies, and therefore the index of refraction is different for red light and blue light. If I take water, the numbers I'm going to give you are for water, then the index of refraction for red light in water is 1.331, but the index of refraction for blue light in water is 1.343. And we're going to use these numbers shortly to get a deeper understanding of the formation of the rainbows that's behind this, of course. And so you notice that the blue light is 1% slower in water than the red light. And this phenomenon that you see there, that the speed of electromagnetic radiation depends on the wavelengths, depends on the frequency, we call that dispersion. It is a good thing that sound in air is not dispersive, because just imagine that high frequencies would travel faster than low frequencies, just as an example, or slower for that matter. It would mean then that if you go to a concert and you would listen to the violins and the bass, that the violins would reach you first, and then the sound of the bass would reach you later. And the farther you are away from the orchestra, the worse that would be. If the effect were very strong, here in 26100, someone sitting in the back row could not even understand my words, because the high frequencies would reach that person at a different time than the low frequencies. So sound in air is non-dispersive. But glass and water are dispersive for light, and it's very noticeable. If I take a piece of glass and I give it this shape, the shape of a prism, and I shine some light on here, light from these light bulbs, or light from the sun for that matter, then I can apply Snell's law here. I know the angle of incidence, theta 1. I know the index of refraction, this is for water, but you can look them up for glass, of course. And then you will see there is a difference of the index of refraction for red light that there is for blue light. And so, when you reach this side of the prism, again you have to apply Snell's law. And when you do that, you will see that the red light doesn't come out at the same angle that the blue light come out, but the two diverge. That is the result of the fact that the indices of refraction are different, but also the result of the fact that we have this particular shape, funny shape, namely that this side of the glass is not parallel to this side. And so if you put a screen here, you will see colors. You can make a spectrum. You can convince yourself that the light from these light bulbs is just not white light, but that it contains many, many colors. Well, it has to contain many colors, because if I look at that gentleman there, he's wearing a red shirt. Where do you think that red color is coming from? Must come from the light bulb, so there must be red light in there. The woman sitting next to him is wearing a green shirt, so there must also be green light in this light. And the same is true for sunlight. But the beauty is that making use of the dispersion, you can decompose the white light into the individual colors and make a spectrum. If you take a piece of plain parallel glass, which is window glass, then you're not going to see colors. Because if now I shine light on here, white light, from the light bulbs or from the sun, it is true that it will obviously refract in here. But when you apply Snell's law again here, then it will come out, all the colors will come out in the same direction. So the red light comes out here, and the blue light comes out in the same direction. And your brains are very special. If your brains see all colors coming from one direction, they say, I see white light. Look at the light bulb. You say, oh, that's white light, but look at this gentleman, you say, hey, it's red. It must come from that light bulb. So your brains are special in the sense that they think that the combination of many colors is white. And I can show that to you in a rather convincing way. You see here a disk, and I would assume that you see colors on that disk. If not, you have a problem. And I can fool your brains. What I can do, I can rotate that disk so fast that your brains get so mixed up that they're going to say to you, yeah, that's white light. So let me first give you some ideal light on that disk, and I'm going to spin it up a little. So you agree with me, right? You still see colors, yeah? Still see colors, right? Okay. You still see colors, right? Yeah. Yeah. This is as white as it can be for me. Not too surprising, right? The same situation when I look at a light bulb. All these colors are processed by my brains in such a way that they think, or they actually make you see white light. It's as real as you can have it. And so this raises the subject of the illusion of colors, which is what I want to discuss with you for the remaining part of this lecture. If you ask a physicist, when do you see certain colors? When do you see red? When do you see blue or green? Then chances are that he would give you a standard answer, and he would say, well, that depends on the wavelengths in air. If you tell me what wavelengths you're on, then I will tell you what colors you will see. And I have here a transparency which makes the connection between wavelength and these colors. It's also on the web, so you can also download this. And so if the wavelength of light in air is about, in this range, 1 angstrom is 10 to the minus 10 meters, yeah, you will probably say that's red light. When the wavelength gets shorter, in this range, you would say, yeah, that's green light. And when the wavelength gets even shorter, you would say, yeah, that's blue light. And you can't see any wavelength shorter than this. You get into the ultraviolet here, and you can't see any wavelengths longer than this. That's infrared, and our eyes are not sensitive for those wavelengths. So this is all nice and dandy, but we still have the problem of the fact that if you mix all the colors together, like the rotating disk, and like looking at the light bulb, that our brains still tell us that we are seeing white light. So maybe matters are not really as simple as we think.
Total internal reflection, as its name suggests, means that a ray of light is reflected inside of an object. Totally internal reflection. This means that at a critical angle where the refraction angle is greater than 90 degrees or 90 degrees or greater, it means it's pointing all along the surface of the material and it's directed. Now there's nothing going to be refracted out of the material. It's only going to be reflected back into the material. Internal reflection only happens when a ray of light goes from a medium of high index of refraction to low index of refraction. So it moves, and the critical angle is this angle where it happens. Since the sine of 90 degrees is equal to 1, the critical angle, the sine of that critical angle is equal to the index of refraction of the medium 2 divided by the index of refraction of medium 1. And index of refraction of medium 1 is always greater than medium 2. One major application of this is through fiber optics, where a light beam, which is something that carries information, is projected through something, and you use this in cameras a lot actually. And it's projected, and you can bend it around something where there is a core material that allows the light to be reflected back and forth, and it has a higher index of refraction than the outside material. And this is used, colonoscopies or cameras, a lot of internal cameras that you use in medical research, or any camera that has like a cord. It actually, you can bend it around and the light is still reflected into the material so that you can see it. Fiber optic cables are used in a lot of information transfer throughout both within our country and across wide spaces. There are different advantages as opposed to satellite communication. Cost and maintenance of, or the initial cost of putting a cable, just stringing it underwater. They have a lot of ships that do this. It probably is becoming closer and closer to the cost of building a satellite, but a satellite is still way more expensive. And there is really no significant advantage besides the processing speed, or there wouldn't be much difference between the information transfer themselves. It's more just the maintenance of these different types of cables and information transfer. Diamonds have a very high index of refraction, and once if you are a skilled jeweler or a diamond cutter, you cut a diamond in a specific way so that the light, once it enters the diamond, will internally reflect all around there inside of it, and gives it that kind of sparkle appearance where the light just looks like it's trapped inside a diamond. And so that's why it's important to cut them in a certain way so that the light will continue to reflect inside of it. Dispersion is this spreading out or separation of colors within light. And this is what Professor Lewin talked a little bit about, how the index of refraction depends on the wavelength. And because it has a slightly different index of refraction, it will bend a little bit more, or bend a little bit differently. And therefore, it will give that rainbow effect. That's how we get the idea of rainbows or any other types of spreading out of light within prisms. So here we have a couple of different wavelengths with respect to glass and in air for different colors of light, and it shows the difference, the changes in the index of refraction. And the index of refraction change is very small, from red to violet or purple. It's 0.018, so it's not a large change, but it is enough of a change to cause the angle to change by about a quarter of a degree or so, about 0.3 of a degree, somewhere around there, a little bit more than that. But that means is what actually causes the rainbows that we see on a daily basis.